In this video, I would like to do a hypothesis test for a population mean single sample when sigma is unknown. When home runs abound in baseball, there are often charges that the new baseballs are juiced, quote unquote, to travel farther. Tests of the old balls show that when dropped 24 feet onto a concrete surface, they bounced an average of 92.84 inches. In a test of 40 new balls, that should be plural, the bounce heights had a mean of 92.64 inches and a standard deviation of 1.79 inches. Use a level of significance of 0.05 to test the claim that the new balls have a bounce height different from 92.84 inches. Phew, that was a mouthful. All right, this is a hypothesis test for the mean when sigma is unknown. Nowhere in the wording of this problem does it say that we are to assume the population standard deviation is any particular value. What we have is the sample standard deviation because it comes from the sample of 40. If they said assume the population standard deviation is any particular value, we would be using a z-test. Now the conditions are met to use a single sample t-test because our sample size is more than 30. All right. The first thing we want to do is we want to identify the claim in terms of the population parameter mu. It says the claim is that the new balls have bounce heights different from 92.84. Okay, that would be the average bounce height. So mu compared to 92.84, there is no sense of direction or inequality implied here. Different would be not equal. So this is the claim. Because the claim does not contain the case of equality, the claim is the alternative. So this makes the null equal to 92.84. If you're taking my class currently, the textbook I'm using just uses equality in the null. Other textbooks would use the complete opposite case if this were a single-tailed test. But equal versus not equal is fine for this problem. Just remember that the case of equality always belongs in the null. Because the population standard deviation is not known, and we're testing the mean, and we're given a sample size more than 30, the conditions are meant to use a t-test. Our standardized test statistic, again I like to use an asterisk for my test statistic, follows the same structure as the test statistic standardized does for a z-test. It's what we observe, our point estimate, which is x bar, minus the claimed or the hypothesized parameter, over s over the square root of n. Now this s is the sample standard deviation. Why are we using s? Because we do not know the population standard deviation. All we are given in the problem is the sample standard deviation. So plugging the information into the problem, from our sample of 40, the mean, which would be the sample mean, is 92.67. And I want to subtract the claimed value. This is the average height for the set of old balls. So that would be 92.84. Okay, there is a difference between the two, but we want to know, is this difference statistically significant? It is larger, so if we were just making the conclusion based on the point estimate alone, being juiced to go farther Because this is greater, someone might come to that conclusion. But to appropriately make that decision, we need to standardize and compare it to the critical values from the t-table. All right, so we want to take that and divide it by the sample standard deviation, which is 1.79, over the square root of the sample size. And again, that was 40. So getting my calculator out, turning it on, which is always helpful. I'm going to put parentheses around my entire numerator expression and my entire denominator expression, just to make sure I get the correct value from the calculator. All right, so I get a standardized test statistic of negative 0.601, rounding to 3 decimal places. Now remember, the t-distribution is bell-shaped with a mean of 0, but its exact shape, even though it's bell-shaped, its exact look depends on the degrees of freedom. The smaller the sample size, the shorter and heavier, the shorter the bell and the heavier the tails will be. So to find the 2 critical values, and we know that there's going to be 2 because this has a not equals in the alternative, it makes it a 2-tailed test. To find those critical values, we need to figure out how much area is in each tail. And to do that, we need to divide alpha by 2. So I know I'm going to have 2 critical values. Alpha is equal to 0.05. So dividing alpha in half, that's going to be 0.025. And this is the amount of area in one tail. All right, so sketching a bell-shaped distribution. It's not standard normal, but it is bell-shaped. You can think of the t-distribution as the normal distribution's little sister. Shading 2 areas of rejection. I want 0.025 amount of area in each tail. To get the critical value, you want to go to your t-table. You could use your inverse t function in your TI-84 if you have a newer TI-84, and I do have that example in one of my previous videos, and you are welcome to take a look at that. But for this example, I'm going to use the t-table. So the printing of this is kind of small. Unfortunately, I have a hard time reading this, even with my bifocals. All right, so I have 0.025 amount of area in each tail. My degrees of freedom is going to be 39. Remember, the degrees of freedom is n-1. And reading over the top of the table to 0.025 and down to 39 degrees of freedom. Oop. Oh shoot, this one is not in the table. My apologies. I happened to pick an example that doesn't have 39 in the table. But what I do know is that 39 is reasonably close to 40. So I'm going to consider this critical value to be approximately 2.021 for the upper. And by symmetry, it's going to be negative 2.021 for the lower critical value. The t-table in the textbook I'm currently using does not give negative t-values, but you can easily figure that out because the t-distribution is symmetric. Now let me get that critical value exactly. So if you do have a newer TI-84, you want to go to your distribution menu, and because you're given an area or a probability first, and alpha is a probability, you want to use an inverse function. So option 4 is inverse t. It needs a cumulative area as its input. I could use this lower critical value, this lower tail area, 0.025, and it needs the degrees of freedom, which is 39. Alright, so a little more accurately, this lower critical value is going to be negative 2.03. Oops. Oh, that's correct. My apologies. Which is reasonably close to the critical value I got when I used the table. And by symmetry, this upper critical value will be positive 2.023. All right, so I need to take a look at where my standardized test statistic lies. Is it further out in either of these tails in a rejection region? Or is it in between the critical values in the fail to reject region? Negative 0.601 is somewhat close to 0. And I can see just by the placement of it, we are well in the fail to reject region. So going back to my null and my alternative, I'm failing to reject the null, meaning that if I circled the one that quote-unquote wins, I would be circling the null hypothesis. The claim is the alternative, and we did not reject the null, so we are not in favor of the alternative. So to answer the question, or to address the claim is that the new balls have a mean bounce height different from 92.84 inches. Well, because we are failing to reject the null, and the null contains the case of equality, there is not enough evidence, or there is insufficient evidence to support that claim being that the mean height is different from 92.84. So the correct way to word this is that there is insufficient evidence to support the claim that the new balls have a mean bounce height different from 92.84 inches. So going back to the beginning of this problem, whether or not the balls are juiced to travel farther, there wasn't enough evidence to say that the mean bounce height is different from 92.84. So to say that the balls are juiced is not supported based on this sample. Now this is the critical value method. Let's take a look at the p-value. And to get the p-value, we're going to need to use our technology. The reason why is that the t-table is limited. And if I were to use the t-table to get the p-value, all I'm going to get is a range of values for the p-value. So the p-value, again, is the probability of getting a test statistic at least as extreme as the one obtained by the sample. It is an area. When we're using the p-value method, we're comparing it to alpha. When we're using the critical value method, we're comparing the test statistic in standardized form to where it's placed with respect to the critical value or values along the horizontal axis. No matter what method you choose to use or you're instructed to use, the decision will be the same. So to get the p-value using the TI-84, and this is also how you would do a single sample t-test in the TI-84, I'm going to go to my Stat menu, right arrow over to Tests, and the second option is the t-test, which is the appropriate test we want to use for this example. And either we'll have the raw data, all 40 bounce heights, or the summary statistics, which is what we have in this problem. This screen is nearly identical to the z-test. It's going to be asking for pretty much the same pieces. It needs the value from the hypotheses, which was 92.84, and the sample mean, which was given to be 92.67. This S sub x is the sample standard deviation. Remember, we don't know the population standard deviation, so we need to use the sample standard deviation in the formula. Our sample size is 40. And here we can change the direction of the alternative if we need to. This is a two-tailed test, so I want to leave it as not equals, and then calculate. You'll see that my standardized test statistic, my t-value, was negative 0.601, which is the same as I got when I did this by hand. And right below it is the corresponding p-value. That p-value is pretty high. Okay, that indicates my test statistic is very close to the mean. So my p-value in this problem was 0.552, rounding to 3 decimal places. And remember, the decision criteria using the p-value method is that when your p-value is greater than or equal to your level of significance, which is alpha, you fail to reject the null. If the p-value is less than alpha, then you reject the null. Okay, so I have a p-value of 0.552, and I have alpha. My alpha given in this problem was 0.05. This is greater than or equal to 0.05. So my decision is to fail to reject the null. Because the decision was to fail to reject the null, it is possible that a type 2 error may have occurred. I'd like to underscore that, because it doesn't mean that it did occur. It means that because our decision was to fail to reject the null, it is possible we failed to reject the null when the null is actually false. So a type 2 error may have occurred.